Hi guys, my name is Addison Altman, and today I'm going over section 9.3, which is molecular shape and molecular polarity. So, polarity basics. So, what exactly is polarity? So, polarity occurs due to an unequal sharing of electrons in a bond. So, a nonpolar bond would be equal sharing of electrons between two atoms, and then a polar bond is just unequal sharing of electrons. So, why do we have equal and unequal bonds? So example of a nonpolar molecule would be oxygen. So electrons are shared equally throughout these two atoms in their bond. And this is because they have the same electron of negativity. So they both pull on electrons the same amount, so they end up canceling each other out and being equal. However, a polar molecule, for example, would be hydrochloric acid. So hydrogen is a lot less electronegative than chloride is. So chloride wants to pull electrons more than hydrogen does. So this is why we get this unequal balance and get a polar molecule. So this forms a bond dipole, which pretty much just shows where electrons are being pulled in a bond. And so in this case, our bond dipole is moving towards the chloride atom because they're pulling the electrons more that way. So we're able to calculate a dipole moment. So this is the overall measure of charge separation in a molecule. So the formula to calculate it equals our dipole moment times the charge separation and then our distance between charges. So the distance between charges would be pretty much just the distance between our two atoms, and then our charge separation is how much bigger one is than the other. And then whenever we calculate this, we have to convert it into divides. I'm pretty sure that's how you say it. And the conversion factor is just 3.336 times 10 to the negative 30th. Then it's just coulombs times meters is our unit on that. So let's just first calculate the dipole moment for hydrochloric acid. So our bond length was just given to us, and it's 127 picometers, which is 1.27 times 10 to the negative 10th meters. So oh my gosh, my thing is just not. So whenever we want to solve these, we always want to convert our bond length into meters. So that is just something to keep in mind. So most of the time you will be given very, very small bond lengths, and you always have to convert to meters. And then our charge separation was 1.6 times 10 to the negative 19th. So that's just the difference between those charges. And then pretty much the math for this unit is very simple, and you just multiply the two together, and that gave us 2.03 times 10 to the negative 29th coulombs times meters. But we always want to convert into divides. I'll learn how to say it eventually. So we'll just convert by dividing by that constant. And then we got 6.1 as our dipole moment, and that is moving towards the chloride atom, not the hydrogen. So we can also, the two biggest factors in bond dipoles. Sorry, this dog is actually insane. I'm dog sitting. Is either the difference between individual atoms, so that individual bond dipole, but then we also have something called molecular polarity. So this solely depends on the shape of the molecule, the shapes that are all discussed in 9.1 and 9.2. So symmetrical molecules have dipoles that cancel each other out, so they have a net dipole moment of 0, so they're nonpolar. But asymmetrical molecules have dipoles that do not cancel out and have a net dipole moment of some number. So these are our polar molecules. So for example, a nonpolar molecule would be water. So we can individually look at each of these. So we have our carbon-oxygen bond, and we can see that oxygen is more electronegative, so the electrons are moving this way. But because of its linear shape and these two dipoles are pointing in opposite directions of equal magnitude, because these are the same bonds, we have a net dipole moment of 0. But say over here this was, say, another carbon. So we have an oxygen carbon-carbon bond. It would end up being a polar molecule because this oxygen-carbon dipole moment will be greater than what we would have over here. Then we have polar molecules. So, for example, oh my gosh, this over here was CO2, not H2O. This was not water. But when we have H2O, it has that bent shape. So even though you might think that, oh, it only has two things bonded to it, it might be a linear shape. This is why the geometric shapes matter so much, because when we look at it, both of their dipoles are pointing towards the oxygen molecule because the oxygen is more electronegative. But these don't cancel out because they're not in opposite directions. So we have our net dipole moment going straight up, pointing towards those two unbonded pairs of electrons. So we have to look at, for all of these molecules, at the shape. So if you get confused on the shapes, I recommend watching the 9.1 and 9.2 models, because that is pretty much the driving factor of your dipole for molecules that have 3 or more atoms. So for some of these, they would cancel out, like say our octahedral, say these were all the same type of atom out here, we would end up getting things that cancel out, so the net might be 0. However, in shapes like the T shape or the seesaw, they wouldn't cancel out in the same way because they are not directly symmetrical. Usually the easiest one to know that it is nonpolar are linear ones where both these X's are the same type of atom, that you know they'll be the same dipole for each individual bond, so it'll end up canceling out and having a net dipole moment of 0. You won't be really expected to do a ton of calculations on this. It's more just knowing whether a molecule is polar or nonpolar and the theory behind it. So yeah, that's my video. There wasn't really much to this unit, but good luck.